Welcome to AI Paper Slop. If you're an ML engineer or a researcher trying to figure out how to actually scale robotics, you're in the right place.
Yep, our mission here is always zero fluff, just breaking down the absolute latest technical AI research for you.
Exactly. So let's just dive right in. Today we are looking at a paper called, let me get the exact title, Xiaomi-Robotics-1, Scaling Vision Language Action Models with over 100K hours of real-world trajectories.
It is a massive paper.
Yeah.
And I mean massive in every sense of the word.
Yeah, so to give you the 60-second summary right up front, robotics has been suffering from this just huge data bottleneck, right? Traditional teleoperation is slow, it's expensive, and it is completely hardware-bound.
Right, you're usually limited to how fast a human can safely puppet $1 million robot arm.
Exactly. But the researchers at Xiaomi basically bypassed that entirely. They pre-trained a vision language action model, a VLA, on over 100,000 hours of real-world data.
Which they collected using UMI, or Universal Manipulation Interface, handheld grippers.
Right, and to handle that insane amount of data, they built an auto-labeling pipeline using Qwen 3.527BB to annotate trajectory segments as state transitions.
Yeah, and then they fed all that into a mixture of transformers architecture, hooking up a pre-trained vision language model with a diffusion transformer.
Using flow matching, which we will definitely get into. Then after all that pre-training, they did post-training on 10,000 hours of cross-embodiment robot data to, align it to imperative instructions.
And the result? Highly predictable scaling laws for physical robotics, just like we see in LLMs, plus state-of-the-art performance on benchmarks like RoboCasa365 and RoboDojo.
It is wild. The sheer engineering execution here is it's what really makes this paper stand out.
Oh, absolutely. I mean, we've seen VLA models proposed before, but this research systematically just deconstructs the physical and computational barriers.
Right. So let's talk about that scale first, because that's what immediately jumped off the page for me. 100,000 hours of physical interaction data.
It's basically unprecedented.
Yeah, like for context, if you've worked in robotics, you know that gathering even 1,000 hours of high-quality teleoperation data usually requires millions of dollars.
Yep, and a whole fleet of robots constantly breaking down.
Right, plus constant human supervision just to handle safety resets. So how do they actually acquire 100,000 hours without bankrupting themselves?
So the trick was they just abandoned the robot hardware entirely for the data collection phase.
Oh, wow. Just skipped it.
Yeah, they used the Universal Manipulation Interface, the UMI. So if you haven't seen one, you can picture UMI as basically a set of handheld mechanical grippers.
Like a claw on a stick.
Yeah, pretty much a high-tech claw on a stick with egocentric cameras mounted directly on them. There's no robot arm attached at all.
Okay, so instead of sitting at a desk with like a VR headset or some complex joystick, trying to remotely drive a bulky metal arm to pick up a coffee cup.
You literally just hold the gripper yourself.
Right, you're just walking through your own house, grabbing the cup with this handheld claw, and the camera is just recording the visual stream from the claw's perspective.
That is a core mechanism. And because the setup is portable and totally untethered from a lab, they could scale data collection out into the real world really fast.
So they weren't just in a sterile white room.
No, not at all. The data set spans households, industrial sites, offices, even outdoor environments.
That is incredible.
Yeah, we were looking at 1.7 thousand unique scenarios, 2.4 million individual episodes, and over 260 distinct manipulation tasks.
Okay, so that solves the video and the motion capture problem. But if you're training a foundation model, raw video and gripper coordinates are kind of useless without semantic labels, right?
The model needs to know what it's looking at.
Exactly. Doing that manually for 100,000 hours of video sounds like, that sounds like a punishment from Greek mythology.
It would take forever. It would be totally computationally and financially prohibitive to use human annotators for that.
So how did they do it?
To bridge that gap, they architected this highly optimized automated labeling pipeline.
Using Qwen, right?
Yeah, but instead of trying to have an AI watch a continuous video stream and guess where a task begins and ends, they simplified the problem.
Yeah.
They just sliced the massive data set into fixed-length video segments.
Oh, okay, so just uniform chunks.
Exactly. Then they fed those specific segments into a powerful large language model, Qwen 3.527B, to generate text captions.
I really want to dig into the system design of that pipeline, actually, because processing that much video through a 27 billion parameter model is no small feat.
No, it's a massive I/O bottleneck usually.
Right. And the paper mentions a producer-consumer setup. How did that actually keep the GPUs fed?
So decoupling the data processing from the inference was their main optimization there. They assigned CPU worker threads to act exclusively as producers.
Okay, so what are the producers doing exactly?
These threads would just rapidly cut the video clips and write them to an in-memory file system. So that acts as an ultra-fast staging area.
Ah, so they aren't waiting on slow disk reads.
Exactly. Simultaneously, you have client threads acting as consumers, pulling those clips from memory and keeping hundreds of Qwen 3.5 inference requests in flight at the exact same time.
That is super clever.
By isolating the video decoding from the LM inference, they basically eliminated the I/O bottleneck. They processed the entire 100,000-hour corpus in roughly 2 weeks.
2 weeks, that is insane. But there's a really fascinating detail in how they prompted that LLM during the labeling phase that I want to bring up.
The state transitions.
Yes, the researchers specifically instructed Qwen to label these segments as state transitions rather than instructions.
Right, which is a huge shift.
So instead of generating a label that says, pick up the blue cup, the model outputs something describing the change in state, like the blue cup is on the table and now the blue cup is in the gripper.
Yeah.
Why avoid giving the model a direct instruction? Because later on, we obviously want to give the robot instructions.
It represents one of the most critical philosophical shifts in their pre-training strategy, actually. Think about the physics of the real world.
Okay.
If a data set is labeled with the imperative instruction, pick up the cup, the label describes the human's intent, right? But it totally glosses over the complex mechanics required to achieve that intent.
Oh, I see. It doesn't explain the how.
Exactly. By enforcing a state transition framework, the semantic label acts as a highly constrained physical description.
It forces the foundation model to correlate the visual changes, like how a scene transforms from state A to state B, with the physical movements of the gripper.
Right. It's learning physics, not just commands.
That makes a lot of sense, because if you just say pick it up, the model might learn a really shallow mapping, just a picture of a cup and a sudden upward movement.
And that won't generalize at all.
Right. But by describing the states, you're teaching it the geometry of the approach, the contact dynamics, how objects occlude each other. You're essentially teaching the model a generalized physics engine.
Yeah, before it ever has to think about a specific robot arm, it understands physical manipulation at a foundational level.
So once it understands how the physical world reacts to intervention, mapping that to a specific robotic task later on becomes way easier.
Significantly easier.
Okay, let's follow that data into the architecture itself, because this is where the nuts and bolts get really interesting for the ML engineers listening.
The MOT setup.
Yeah, we have this massive data set paired with rich state transition labels. How is the neural network structured to actually process visual semantics and physical joint movements simultaneously?
They implemented a mixture of transformers architecture, often abbreviated as MOT.
So a dual system approach.
Exactly. It couples a pre-trained vision language model, they used Qwen 3 VL for this, with a diffusion transformer, or DIT.
So they are cleanly dividing the labor here. The VLM is doing the perceiving, and the DIT is doing the moving.
That is the functional breakdown, yeah. The VLM serves as the semantic brain. It ingests the raw visual observations from the cameras and the language prompt.
And what does it output?
It processes those inputs and outputs a key value cache, or KV cache, which contains the rich semantic representations of the scene.
Okay, so the VLM builds the context.
Right. Then the diffusion transformer takes over for the physical execution. The DIT conditions its generation on two things. First, the robot's current proprioceptive state, meaning the real-time physical coordinates of its joints.
And second,
that KV cache provided by the VLM. Using both of those, the DIT generates the physical action chunk.
And to generate that physical action chunk, the paper specifies they're using flow matching.
Yes, which is super important here.
For listeners who might be familiar with standard diffusion models, the stuff used in image generation, how does flow matching apply to generating physical robot actions? I see they mentioned sampling a time step tau from a beta distribution.
So flow matching is a generative framework that shares DNA with diffusion, but it often provides a more direct mathematical path to mapping a simple noise distribution into a complex target distribution.
And the target distribution here is what? The actions.
Right. It's the continuous space of expert human trajectories. When training this vector field, the model introduces noise at various time steps.
Okay. Standard diffusion stuff so far.
But by sampling the flow matching time step, tau, from a beta distribution rather than a uniform distribution, the researchers intentionally skewed the training process.
Skewed it how?
They placed heavier emphasis on the noisier time steps during training.
Okay, wait, why focus on the noise? What is the advantage of spending more training cycles trying to decipher a highly corrupted signal?
It forces the model to learn the macro-level structure of the action space first.
Oh, I see.
Yeah, if you focus too much on the clean, low-noise time steps, the model tends to overfit on the micro-jitter of the specific trajectories.
Like it gets obsessed with the tiny shakes of the human hand.
Exactly. By heavily weighting the noisy time steps, the model learns the broad generalized stroke of the movement, like reaching across the table before it refines the sub-millimeter precision of the grasp.
That is brilliant. But, and here's the catch, training a diffusion transformer from scratch to interpret a KV cache is notoriously slow.
Very slow.
The researchers didn't just leave the VLM alone, right? They introduced an auxiliary action generation supervision during training.
Yes, using something called choice policies.
Choice policies. How does that accelerate the DIT's learning?
This is a really cool systems optimization. A standard VLM is optimized to output text describing a scene, right?
Yeah.
But the DIT needs representations optimized for movement. To bridge this, they forced the VLM to predict K-candidate action chunks itself.
Wait, the VLM predicts the physical actions?
Yes, it predicts candidate chunks. The system then evaluates those K-candidates against the ground truth expert action using a winner-takes-all L1 loss approach.
Okay, by winner takes all, you mean the system only backpropagates the loss for the single candidate that was closest to the correct action and just ignores the rest?
Correct. The candidate closest to the ground truth receives the penalty and optimization.
And why do that?
It steers the internal representations of the VLM away from purely passive, descriptive features and molds them into action-oriented semantics.
Ah, so by the time the VLM passes its KV cache to the DIT, those representations are already highly optimized for physical execution.
Exactly. It gives the DIT a massive head start.
Here is where I see a potential flaw, though. And let's use an analogy. Think of the VLM as a senior architect sketching out a really detailed blueprint to speed up the construction process.
Okay, I like where this is going.
But if the builder, the DIT, just blindly copies the architect's sketch, the builder never actually learns how to build a house from scratch.
Right.
If the VLM is already doing the heavy lifting of predicting actions to optimize its own representations, won't the DIT just look at those action predictions in the KV cache and copy them?
Yes, it absolutely will.
It seems like it would just get lazy and stop grounding its own movements in the raw visual data.
You have identified the exact shortcut learning failure mode the researchers encountered. Neural networks are incredibly efficient at finding the path of least resistance.
They really are.
When the DIT's attention mechanism was allowed to see the action-related tokens generated by the VLM within that KV cache, the DIT simply memorized them.
It just cheated.
Yeah, it stopped learning the complex vector fields required for robust flow matching because the VLM was essentially handing it the answer key.
So how do you fix a lazy neural network in this scenario? Do you just turn off the choice policies?
No, you use attention masking.
Oh, of course.
The researchers explicitly modified the architecture so that the DIT's tokens are blocked from attending to the VLM's action-specific tokens.
So it can't see the answers.
Right. The DIT is still allowed to look at the rich semantic representations of the visual scene and the language instruction, which have been sharpened by the choice policy optimization, but it is blind to the actual action predictions.
This is a very elegant way to get the best of both worlds. You get the optimized representations without the lazy shortcut.
It forces the DIT to do the hard mathematical work of grounding its flow matching generation in the environment.
Okay, so at this point in the paper, the architecture is finalized, and it has been pre-trained on a literal mountain of human-generated UMI gripper data.
100,000 hours of it.
But a human arm holding a stick is fundamentally different from a robotic arm with rotating servos and distinct kinematics.
Very different.
How do they actually bridge the gap from a human walking around a house to driving a real multi-jointed robot?
That transition requires the second stage of their methodology, post-training.
Okay, post-training.
This phase is dedicated to aligning the foundational knowledge to specific robot embodiments. For this, they utilized roughly 10,000 hours of cross-embodiment trajectories.
What exactly comprises that 10,000 hours? Are we back to traditional teleoperation for that part?
A significant portion of it is, yeah. Over 7.2 thousand hours consist of in-house data collected using actual mobile manipulators and dual-arm robots.
Got it.
They combine this with existing open-source robot datasets, as well as a small, instruction-labeled subset of their original UMI data.
Now, this post-training phase seems to have two distinct missions. First, you have to solve the kinematic mismatch. transferring knowledge from a floating human hand to a mechanical arm.
Right.
But second, you have to change how you talk to the model, because during pre-training, everything was labeled as a state transition.
Exactly.
But in the real world, a user doesn't say, the shoes are dirty and now the shoes are clean. They just say, wipe the shoes.
Right. You want to use natural language commands.
Yeah.
So tackling the kinematic mismatch first, they employed a technique called relative delta end effector poses.
Relative delta end effector poses. Break that down for me.
Well, it is physically impossible to map the absolute joint angles of a human shoulder and elbow to the joints of a robotic arm, right? The morphology is entirely different.
Yeah, a robot elbow doesn't bend like mine.
Exactly. Instead, the researchers isolate the gripper itself. They train the model to predict how that end effector of the gripper should move through 3D space relative to its current position.
Oh, I see. So the model isn't outputting commands like rotate joint 3 by 45 degrees.
No, not at all.
It's outputting commands like, regardless of what limbs are holding this gripper, move the gripper 3 inches forward, 2 inches up, and pitch it forward slightly.
That intuition is spot on. By predicting relative deltas, the action generation becomes largely agnostic to the underlying kinematic structure of the arm.
And then the robot's own internal software just figures out the rest.
Exactly. The specific robotic controller handles the inverse kinematics of moving the physical joints to achieve that delta.
That's super clean.
And simultaneously, the post-training phase tackles your second point regarding language.
The imperative instructions.
Right. By mixing in data annotated with imperative instructions, the wipe the shoes prompts the model learns to bridge the gap. It maps the human's imperative command to the deep state transition physics it mastered during pre-training.
Okay, so the two-stage recipe is complete. But let's look at the title of this paper again, because it's explicitly called Scaling Vision Language Action Models.
The scaling laws, yes.
In the LLM space, the scaling laws are practically dogma at this point. If you increase the parameter count and increase the pre-training data volume, the loss decreases on a highly predictable curve.
We've seen it time and time again.
Right. So for the ML engineers listening who are trying to allocate resources right now, did Xiaomi actually prove that this holds true for physical robotics?
They did, and their ablation studies on this are incredibly thorough. They isolated both the data axis and the model size axis to measure the distinct impacts.
Okay, let's start with the data scaling.
Looking at data scaling first, they isolated a 20,000-hour subset of the UMI data. Then they pre-trained separate models on 12.5%, 25%, 50%, and 100% of that specific subset.
Interesting. When you restrict a model of this size to only 12.5% of the data, what does the loss curve actually look like?
You see classic overfitting. At the 12.5 and 25% thresholds, the validation error initially dropped as the model learned basic patterns.
But then it spikes.
Yes. Then it sharply spiked as training continued. The model lacked the environmental diversity required to generalize, so it simply memorized the training trajectories.
So it just learned how to do those specific tasks in those specific rooms.
Exactly. However, when they scaled up to the 50% and 100% thresholds, that validation loss stabilized and showed a continuous monotonic decrease.
A decreasing loss curve in a simulated environment is great, but does it translate to a robot actually succeeding in the physical world? Like, does it actually pick up the cup?
The transfer was direct and measurable. They ran those pre-trained models through the post-training alignment phase and deployed them out of the box in unseen environments.
Then what were the numbers?
The model bottlenecked at the lowest data subset, achieved a success rate of 53%.
Okay.
The model exposed to the full 100% data subset jumped to a 75% success rate.
Wow, that is a staggering performance gain purely from data volume.
That's massive.
What happens when you scale the architecture itself, though, that making the neural network wider and deeper yield similar jumps?
They evaluated 2 billion, 5 billion, and 10 billion parameter variants of the model.
Okay.
The success rates did climb monotonically. It was 61% for the 2B model, 75% for the 5B, and 79% for the 10B variant.
This is the million-dollar question for anyone managing a compute budget right now.
I know exactly what you're going to ask.
If you have finite resources, do you spend it spinning up a 10 billion parameter model? Or do you keep the model small and spend the budget deploying humans to collect more UMI data?
The data dictates the strategy here.
Yeah.
While increasing model capacity from 2B to 10B yielded an 18-point improvement, the researchers note that the performance gap between model sizes is actually less pronounced than the gap observed between data scales.
So data wins.
Data wins. Their conclusion is that once you reach the billion parameter scale, the neural network's capacity is already largely sufficient to capture the complexity of the existing data distributions.
The model is smart enough, it just needs more to look at.
Exactly. The true bottleneck for modern robotics is data volume and data diversity. If you are forced to choose, prioritize massive, diverse data collection over simply inflating parameter counts.
Which completely validates their initial massive investment in the 100,000-hour UMI dataset in the first place.
Totally.
And because that foundation is so robust, the sample efficiency for learning brand new tasks is incredible. The paper highlights fine-tuning the model on less than 10 hours of demonstration data per task.
Less than 10 hours of data in physical robotics is an extreme low data regime. Historically, a model would fail to learn anything meaningful from such a small sample.
Right, it would just flail around.
Yeah, but because of the robust pre-training, Xiaomi-Robotics-1 achieved an average success rate of 75% across 4 highly complex dexterous manipulation tasks using only that tiny sliver of fine-tuning data.
That's crazy. How does that compare to other models?
They benchmarked this against the Pi 0.5 model, which is a very capable open-source baseline. In that same low data environment, Pi 0.5 only managed a 40% success rate.
So it's nearly double the performance. And that sample efficiency translates directly to standardized benchmarks as well.
Oh, yeah.
On RoboCasa365, which evaluates complex, multi-stage household tasks, this model hit a 57.6% success rate, obliterating the previous state-of-the-art of 46.6%.
A huge leap.
And on the RoboDojo benchmark, it scored an average of 20.07, pulling far ahead of the previous record of 13.07. But the test that really stands out to me is the long horizon suitcase packing task.
Oh, that task is the ultimate proof of their methodology.
What did I have to do?
The robot had to navigate a room, identify specific clothing items, grasp them, and meticulously pack them into a suitcase over a continuous 10-minute horizon.
10 minutes of continuous action without a reset.
Yes. Maintaining a generalist policy without succumbing to a catastrophic failure or compounding positional errors over 10 continuous minutes is an incredible demonstration of real-world stability.
It really proves the relative delta-end effector approach works flawlessly, even over extended timeframes.
It absolutely does.
So, to summarize this massive achievement, the researchers at Xiaomi solved the historic robotics data bottleneck by realizing they didn't need robots to collect data.
Yep, just ditch the robot.
They scaled to 100,000 hours using cheap portable UMI grippers. They leveraged Quen to auto-label the physics of state transitions, fed it into a mixture of transformers that forces the diffusion transformer to ground its own generation, and proved that robotic models scale just as predictably as LLMs if you feed them enough diverse data.
It provides a highly replicable, highly scalable blueprint for building the next generation of robotic foundation models.
But this brings up a really provocative thought to leave you with as you think about the future of this field.
Okay, let's hear it.
The overwhelming success of this model is predicated on capturing human-centric motion data and translating it to robotic actions.
Right.
If the brains of future foundation models are going to be trained almost exclusively on unconstrained, human-generated UMI trajectories, because teleoperation is simply too expensive, how is that going to dictate the physical hardware design of our machines?
Oh, wow. That is an interesting point.
Right. Like, will engineering teams stop designing robots based on pure mechanical and industrial efficiency? Will the industry pivot to designing robots that perfectly mimic human morphology simply because a humanoid robot can most perfectly execute the motions found in these massive human-generated data sets?
Form-following data instead of form-following function.
Exactly. It is a fascinating hardware question driven entirely by a software data bottleneck. Definitely something to mull over as you build out your next pipeline. Thank you for joining this session on AI Paper Slop. We will catch you on the next one.